The following program is brought to you by Caltech.
Okay, our next speaker is Donghai Jeong from Penn State University, and the title of his talk is Signatures of Primordial Gravitational Waves in Large-Scale Structure.
Thank you. Thank you for the invitation. So I changed the gear a little bit and talk about what's the possible signature of gravitational wave in large-scale structure. So here are my collaborators. So Liang Dai is a student at Johns Hopkins, who is sitting right there. And Malcolm Kamiankowski is my former mentor. He's sitting right there. And also Fabian Schmitz, he's now at MPA. So, like anybody else, I'm very excited about this nice power spectrum of B mode gravitational wave. And like we heard in the morning, it could be dust, it could be real primordial signature. But for this talk, let's presume that everything is from the primordial origin, right? That is the starting point of my talk. But I think it's okay as long as it's in the ballpark of like 0.1 to 0.2. I mean, so then we can talk about the large-scale structure signature of primordial gravitational wave. Right. So implication of R of 0.2. So if that gravitational wave really comes from inflation, it implies two things. The first thing is that gravity is quantized with amplitude h squared is nearly Hubble square in the early time. And second thing is that Friedmann equation gives that so the energy scale is proportional to h squared. That means that inflation happens at about 10 to 16 GeV scale. So we do have strong theoretical argument to believe that primordial gravitational wave, if it is detected, is from the inflation. But the one thing that I was very excited about when I heard about this Bison news is that we have a perspective of observationally prove the inflation. So inflation, what it means is the early acceleration of universe, right? And then primordial amplitude of tensor mode is proportional to h squared, which is expansion rate. And if you detect expansion rate at two different locations, what you can do is that you can take the derivative and really observationally tell if a double dot is greater than 0 or not. That means that you can prove if inflation happened or not in the very model independent sense. So if you just do the little math, so the a double dot over a is dh dt plus h squared. So equating this thing greater than 0 means that this guy, the time derivative of h over h squared is greater than -1. So if you do that, that's the observationally proving that inflation really happened in the early time. So in terms of the language that people talk about, NT, the primordial tensor index, so that is a little bit complicated because you have to relate the d log k to d log a. But then anyway, you can write down this equation. So this is requirement is that NT is greater than -2 over this number, d log h over d log a. So this is a much loose requirement than people talk about the slow roll requirement, for example, that requires NT is very, very, very close to 0. But as long as NT is greater than this value, I think we can say that inflation really happened in the early time. So the key point here is that to do that, we need to measure this primordial amplitude at two different scales, right? What's the perspective of doing that? In CMB, it's quite limited, although it's very great. On large scale, if you go to small l, we have a cosmic variance. And on small angular scale, if you go to larger l, we have a weak lensing. So then here's what I can contribute. What about large scale structure? So large scale structure prove different scales, right? And also, the systematics that affect the large scale structure observables are completely different from systematics that affect CMB. So that's the motivation that I go out there and search for the possible signature of gravitational wave in large scale structure. So this is the placeholder to say that my gravitational wave is same as your gravitational wave. This is a phase part of metric perturbation, which is traceless and transverse. And we have these two modes, H plus and H cross. And also, this is a placeholder to show that my power spectrum of gravitational wave is same as yours. That's the Hij. Sometimes you have a factor of 4 difference, but that's my definition of power spectrum. So there are 3 places that we can look at the signatures of gravitational wave from large-scale structure. First one is the clustering of galaxies, and second, the distortion of shapes of galaxies called weak lensing or cosmic shear. So here we look at how galaxies are distributed, and here we look at how the shapes of galaxies are correlated. And the third one is a fossil memory at the off-diagonal correlations. That is a very new thing that has developed by Mark Kalyankowski and me. So I'll talk about three things one by one. So gravitational wave can affect both clustering at the source and the line of sight path. But then for all of these 3 effects, the source effects are dominant effects because once coming inside the horizon, gravitational wave propagation is described by Klein-Gordon equation, and without the source term, this thing just simply decays away. So gravitational wave, as time goes by, amplitude decays. So the dominant effect for all of these 3 cases are coming from the source location where the amplitude of gravitational wave is largest. So let me start from the effect of gravitational wave on galaxy clustering. So now I'm imagining the universe, or galaxy power spectrum in the universe where it is only filled with the gravitational wave. This work is done by these people and me. So because gravitational wave is a tensor wave, and in the linear theory, there's no correlation between tensor and scalar, the effect of gravitational wave should come from the projection effect, meaning that the difference between the real position of galaxy and the observed position of galaxy. Let's suppose we have galaxy here. And the light from the galaxy is distorted and following this geodesic. And geodesic is not the same as straight line. And then by the time we observe this, we recorded the angular position of this photon that we observed and charted this guy here according to the observed galaxy redshift and the angular position, which is, of course, different from the original position of galaxy. And then how much they differ, we can calculate from the geodesic equation. So that is just integrating out the geodesic equation starting from the observed location to the end point where we achieved, where we reached the observed redshift that we recorded, and we divide it by line of sight component and the perpendicular to line of sight component. So line of sight distortion has 2 terms. This one is time delay and the displacement along the line of sight. And this term is the redshift distortion part due to the gravitational wave. Because because we need only one scalar, that's the H parallel, which is Hij projected onto the line of sight. All of this thing is depending only on the H parallel. In the perpendicular direction, we have this expression that is looks similar to the weak lensing expression that we usually see. And because of this distortion, we have first effect. The first effect is the volume distortion. So because the coordinate here is different from the charting here is different from the original coordinate, then we have distortion in the volume. The volume that we observed is different from the volume out there. So that introduced a first volume distortion effect that can be calculated by requiring that the number of galaxies inside of observed volume is same as number of galaxies inside of the intrinsic volume. And second effect is redshift perturbation. So this is related to how we measure clustering. So we measure clustering. Measuring clustering means that measuring the density contrast. And density contrast is defined as excess number of galaxies compared to cosmic mean. And how do we measure cosmic mean? We measure cosmic mean by adding up all the galaxies at the same redshift, right? But then if your redshift measurement is systematically off by a certain number due to gravitational wave, and that put your galaxies in the superiously underdense or overdense region. So the change in the redshift introduced additional clustering that is proportional to the BE. This BE parameter is the number density evolution of mean number density of galaxies. So if your mean number density of galaxies is constant over redshift, there's no effect. But if you have more and if you have evolving number density of galaxies, and redshift error can introduce second effect of clustering. And third effect is magnification. In the usual galaxy survey, we have certain cut of magnitude or the certain brightness of galaxies that you can measure. But then gravitational wave introduce the changes in angular diameter distance or the luminosity distance that has yet additional clustering introduced by gravitational wave that is proportional to the slope of your luminosity function, how many more galaxies or less galaxies you have if you change the magnitude cut. Those three effects combined gives us this equation that is the clustering of galaxies in the presence of, and only in the presence of gravitational wave. And here, everything is written in terms of h parallel, but they have one term, which is the observer term. That's a 5/4 of h parallel at the observer location. This term turns out to be very interesting because if I plot the angular correlation function of galaxies with only gravitational wave, so this is a L equal 2 mode, and then we got this curve. But then, that is the term, the measurement, the calculation we had without this observer term. But soon after we include the observer term, this contribution dropped down, and then we got the continuous curve. And what it does is the observer term ensures that there is no superhorizon influence of the gravitational wave clustering. So here I plot the contribution of L equal 2 mode from different terms. So we have the term proportional to h parallel and h parallel prime, and this weak lensing term, and this observer term. Without having this observer term, all of this contribution all of this term has a contribution from the very long wavelength mode, means the k very, very small. But then the total, including all of these four, has zero contribution from the superhorizon mode. So that means that each individual contribution of this galaxy clustering term get the contribution from superhorizon mode. But at the end of the day, if you add up all the contribution, including the term at your observer location, then you get zero influence from the superhorizon gravitational wave mode to your subhorizon clustering. Right, so this has a rich physics, but then unfortunately it's way too small to be observed because, again, the gravity wave decays once gravitational wave coming inside the horizon, while scalar mode is keep increasing. So you always have to compete with a scalar mode, and that is a scalar clustering, and there's a tensor clustering. So it's way, way, way small to be detected. So in the optimal case, so we artificially choose to cross-correlate the galaxies redshift 1 and redshift 4. In that case, there's no intrinsic correlation among scalar mode. And then we also turn off this magnification bias to 1. In that artificial ideal case where this gravitational wave is supposed to be bigger, the scalar contribution, it has like 3 or 4 orders of magnitude bigger than the gravitational wave effect on clustering. So it's negative, so you cannot detect gravitational wave from the galaxy clustering. But don't be too depressed. I have 2 more places to look at. And the second place is the shape of galaxies, and then how those are correlated over the sky. So we call it cosmic rulers, or the covariant formalism for the shape distortion. So here, instead of talking about one geodesic line, we talk about 2 geodesic lines. So let's talk about the guy, cosmic yardstick, which is at high redshift. So this is a yardstick, and there are 2 endpoints. And again, due to the geodesic, this guy geodesic is here, and this guy geodesic is here. But by the time we observe this guy, we only know the angular position and the redshift, and we chart this point here and this point there. That means that the distance of yardstick we measured is different from distance of yardstick that was out there, right? But then we have the covariant formalism of writing this thing on the sky. So first, we get a question that who measured this R0? The most natural way of measuring the size of yardstick out there is the thinking about the observer who is moving with this yardstick, right? And this R0, the intrinsic size of this guy, is given by this formula, right? And then, so this R tilde, which is the measured distance, is easy to calculate because we use our own background metric, and then you just charted this thing according to the observed redshift, and then we just measure the distance. And then the difference between this R tilde and R0 can be calculated once you know the geodesic deviation. So here I include all the metric perturbation like A and B and Hij, not only gravitational waves and the scalar and vector mode, just to show that I have this complete formula. And then here again the parallel and perpendicular directional displacement can be integrated if you know the metric perturbation. And now we consider a spherical ruler, means that not just stick, and we think about the sphere, which is perfect sphere, which is out there that we know is a sphere. Then we can parameterize the distortion into 3 different classes depending on its nature on the sphere. So that's the difference between R tilde and R naught. And as a function of observed coordinate difference, and this is only if you have only parallel directional, the line of sight directional distortion, and that is a scalar on the sphere, we call it C. And if this distortion involves one parallel direction and one perpendicular direction, that's a vector on sphere, we call it B. And if it's distorted only along the perpendicular direction, and then we call it A. That A includes the usual magnification and shear. But C and B are also interesting because one reason is that because it's B, the vector mode. The C can be only scalar, but B can be composed by E mode and B mode like we do for the C and B polarization. Then you can have this odd parity part of this B mode that can be also a trace of gravitational wave. That can be a new proof of gravitational wave, although I didn't pursue it along that direction. So we have this complete coherent covariant expression of the C and B and M, and also we have this covariant formula for the shape distortion, the spin 2 shape distortion on the sky if you have general metric perturbation A and B and Hij. So that was not there before, and then we have to do it. And that's just the formalism that I want to show you before I go to the effect of gravitational wave. And then I'll skip this slide, and then I'll talk about the gravitational wave effect on shear. So here I have complicated expression, but I just turn off B and A. Then what I get is this. So here is the usual line of sight integral, the weak lensing formula. And here we have this term which is proportional to Hij at the source location and Hij at the observer location. That has been known as a metric shear and has discovered by these people in this paper. And they describe it as a shearing of the coordinate with respect to the physical space. And we reinterpret this as the following. So to make sense of any weak lensing measurement, we have to define a coordinate system or reference system where the galaxies are statistically round, right? And that coordinate system is, we think, we argue that coordinate system is a local inertial frame along the time-like geodesic of the galaxy. So if you sit in the galaxy, your galaxy looks like circular, right, or round. And then the coordinate around this time-like geodesic is called Fermi normal coordinate. And then coordinate transformation between the Friedmann-Robertson-Walker coordinate and Fermi normal coordinate is given by this relation. And then the shear measured in the local coordinate and the Friedmann-Robertson-Walker coordinate are related by this equation, and we have this one term which is proportional to the Hij at the location of source. That is the metric shear term. And this metric shear term is by far the dominant term. So here I show you 3 different contributions of E mode and the B mode lensing contributions. And then Q2 and Q3 are the line of sight integral form, the integral term, and the FNC term is the metric shear term. For E mode and both E mode and B mode, individual terms are very big, but then if you add up everything, it got decreased, and then total contribution of shear is small. So in particular for B mode, the line of sight term has as large as the FNC term, but then if you add up these two, unfortunately they have different sign and they cancel each other, and then very small contribution of shear. So that has been known before we look at this problem. But then by going to FNC, we found additional contribution. So metric at FNC, which is the local inertia frame, is same as Minkowskian in the zeroth order, and has a correction term, which is quadratic order of XF. Means that if you, as you go outside of your origin, then you have the quadratic deviation. But then if you look at this G00, we have the isotropic component, which is the usual Hubble deceleration. And then we have this guy, which is anisotropic, which is proportional to time derivative of gravitational wave, right? When if you have the perturbations in the 0,0 component of metric can be reinterpreted as a usually gravitational potential. And we have, that means that we have effective gravitational potential, which is anisotropic, and that means we have the tidal field introduced by this gravitational wave. And if you have tidal field around the galaxy, what you have is so-called intrinsic alignment model, meaning that if you have anisotropy in your gravitational potential, your galaxies are preferentially oriented toward the shape of this anisotropic contour. That means that if you have gravitational wave and that gravitational wave has introduced tidal field, then you expect to have additional shear that is introduced by the effective gravitational potential from the gravitational wave, right? And then that intrinsic alignment shear term is proportional to time derivative of gravitational wave. And that term, that is the good news, that term is much bigger than the previously calculated term. So this Lensing term is the term including line of sight integral and metric shear. But if you have intrinsic alignment model with the free parameter, which I choose by 0.1 because that's the intrinsic alignment amplitude of scalar perturbation, and we expect that tensor has a similar kind of correlation. Then you have this as E mode, and that as a B mode. So this is redshift 1 and 2 and 5. But with intrinsic alignment, the signal is much better compared to the without intrinsic alignment case. And as a comparison, here is the uncertainty curve with a half-sky galaxy survey, the weak landing survey with this number density and sigma of 0.3. That is about the same as 3 times as many galaxies that LSST would observe. But that's the good news is that we have some spot in the large-scale structure that we can look for the signature of primordial gravitational wave. By the way, this paper is published in 2012, but back then we still use the fiduciary value of R of 0.2, so I don't have to change anything here. That was the maximum possible value that we thought of back then. But here, because this signal is so small, and we have to worry about the secondary effect, meaning that the nonlinear interaction of scalar can also make the B mode. The scalar cannot generate B mode in the linear order, but in the higher order, you can do it. We look at the 3 things. The first one is the induced gravitational wave, meaning that real second order dynamics of scalar generating gravitational wave, but that is very, very, very small. It's 10 to the negative 14 this level, so we didn't even plot it. And second thing is the second order geodesic equation, meaning that usually in the weak Lensing calculation, we assume that geodesic is a straight line and we perturb it. But then in the second order, we have beyond the Born approximation, there was a calculation done by Hirata and Seljak in 2003 paper, and that we plot here as a purple line. And that is, again, this effect is big on small scale, but drop down on the large scale. And third thing is a reduced shear or lensing bias, meaning that when you measure shear, we are not measuring shear alone. There are always an interference between the shear and the convergence, and then that generates the also B mode, and that is this red line. But on large scale, if you go to large scale, you still have some tensor signal, the weak lensing signal dominating over the second order, the scalar signal. Yeah, so so the summary of this section is that we do have some spot, which is very large scale structure. But unlike CMB, we can do this is only one redshift, and we can do it in the multiple redshifts. So there's a possibility that we detect it in the different redshift. Right, I think this is most promising among three. So that is the clustering fossils from the early universe. That's the work by me and Mark, and also Liang and me and Mark followed up with a more sophisticated case. So idea here is, so we have some off-diagonal correlation. And to talk about off-diagonal correlation, we have to understand what the diagonal means. So in usual cosmology, when you write down the two-point correlation function, we only write down this as a function of R, meaning the separation between, only depend on separation between two galaxies, not depend on where you measure this correlation at, right? And that is the result of statistical homogeneity. And in Fourier space, the fact that this xi does not depend on x is translated as a delta function. Means that if when you correlate two k mode, this is non-zero if and only if we have k plus k prime being 0. And in linear theory and also nonlinear theory, in the nonlinear perturbation theory, this thing is there in the cosmic evolution. Means that we don't have anything that violates the statistical homogeneity in the standard cosmology model. But this thing can be broken if you have two things. So either non-Gaussianity in the very early universe, or the higher the interaction between tensor and scalar. In general, if you have this kind of three-point function, which correlate the two scalar mode to one H mode. So H here is a spectator field that can be anything like scalar, tensor, and vector. But I just write it down as this guy is proportional to the power spectrum of the nuke field, the HP field, and then some coupling constant, coupling amplitude. And to maintain the statistical isotropy, I have to include this epsilon. That's a polarization basis of this guy, and K1i, K2j, and this delta function. So this delta function means that we do not break the statistical homogeneity globally. But if you look at this correlator in the local region around this new field, HP, that three-point function is equivalent to this two-point function, right? With this delta function, but not K1 plus K2 equals 0, but K1 plus K2 plus K equals 0, right? So that is the off-diagonal correlation that what I'm talking about. And the exact formula of this coupling amplitude depends on what kind of non-Gaussianity model you are using or what kind of nonlinear interaction that you're thinking of. But we believe that generally this signature should be there, and then that could be the way that we can prove the primordial gravitational wave. So yeah, this is a motivation of why worrying about new field. And the thing is that in the very early time, the physics can be wild, and you can have additional scalar field and vector field and tensor field. And the good thing about this three-point function is that even though this new field just decay away, the correlation structure of this guy still remains and can give us some imprint as an off-diagonal correlator. So that's why we call it fossil field, because the field itself will just decay away, but we can have this imprint in the off-diagonal correlator. So here, this epsilon ij is a key thing that describes the polarization of this new field, HP. And there are 6 degrees of freedom of polarization, and then they can be scalar and vector and tensor. For scalar case, you have the trace part, and also this looks like tidal field from the one scalar field, and the vector field, which that is one parallel direction to the moving k vector, and also one perpendicular direction, and the tensor field, the traceless transverse part. And then here I have a little movie that this is supposed to be a movie, but now it's PDF, so I have movie in the different file. So here what I'm showing here is that imagine that we have one tensor Fourier mode going to this up direction, and now this surface is a surface of constant correlation function, which is supposed to be just constant. That's supposed to be circular. But because of this tensor field, this constant surface correlation function is distorted quadrupolar way along the perpendicular direction. And if you have scalar mode, then that distortion can be just the isotropic shrinking or expanding of this constant correlation function surface, or like this longitudinal pattern of scalar mode. And for the vector case, we have distortion involved in one perpendicular direction and one parallel direction and one perpendicular direction. So that's the movie that I'm about to show. Where is it? Yeah. So that's the tensor mode. The tensor mode is propagating this up direction. And now we are seeing that the distortion is only in the perpendicular direction. And then it has the quadrupolar dependence. So that means that we have this cosine 2 phi dependence along the perpendicular direction. And for the scalar mode, this longitudinal scalar mode, I don't have to actually show the movie because it's spherically symmetric. But then it's cool to show the movie, right? And the vector mode, that is just one direction, one parallel direction, and one perpendicular direction. So that's it's crossing along this, the sidelines. Anyway, that's the effect. So if you do have the 3-point function that I described, either from non-Gaussianity or from the nonlinear interaction, then we expect to see this kind of distortion. Then how do you estimate that? So we have two-point correlation function, which is non-zero in the off-diagonal, in the presence of H. And then this thing being proportional to the amplitude of the spectator field means that if you can just add up all the delta K1 and delta K2, which add up to the big K, the K of this spectator field, then you can construct an estimator. And then here, important thing is that depending on the nature of this spectator field, or depending on the polarization tensor, it has quite a different azimuthal dependence. Meaning that if you have a scalar field, there is no phi dependence. If you have vector field, we have cosine phi dependence. And if you have tensor field, you have cosine 2 phi dependence. If you have spin 3 field, it has cosine 3 phi dependence. So it's kind of a free way of detecting the higher spin field as well. And then we construct the optimal estimator by inverse-variance weighting this naive estimator of correlating delta of k to delta of k minus k, whose expectation value is 0 in the conventional cosmology. But now we have this non-trivial 3-point function. This thing is non-zero, and we just weighted optimally. And then you get the noise power spectrum. But this is not what you expect to measure because this spectator field is most likely to be a stochastic field. What you want to measure is not just the one wave mode, but the amplitude of spectator field, right? And then we construct this amplitude estimator, which is proportional to this previous estimator square. Means that now we are looking at the non-trivial 4-point function, because one estimator of HP contains 2 delta. Now we are scaling it, so now we are correlating, we are measuring the 4-point function. And then corresponding to this optimal estimator, we can calculate the minimum uncertainty of measuring this amplitude. And this is the plot that I generate. What's the detection limit of this scalar vector and tensor field? And as a function of maximum wave number, and I have two different galaxy surveys. So one is 10 gigaparsec scale survey like this, and this is a 200 gigaparsec scale survey like SKA or Euclid or W1st here. And that this is a line that corresponds to tensor mode of R0.2, right? That means that this thing may not be possible with the current generation of a survey like Sloan Digital Sky survey of 10 gigaparsec cube class, but then it's certainly possible to do it with the next generation of survey like Euclid, W1st, and the like 21 centimeter survey like SKA, right? And even though this is not that sensible, so I think current survey like Sloan Digital Sky survey should put some interesting limit on the amplitude of primordial vector and tensor mode. In particular, vector mode, which is not known so far. So let me conclude here. So I show three different ways of detecting primordial gravitational wave from the large-scale structure. The lesson here is that gravitational wave decays in time and have to fight against the scalar mode. So it's extremely hard to detect it from large-scale structure. In particular, for the galaxy clustering, the signal is very, very weak, so we don't look for the gravitational wave signal there. But for the cosmic shear, in particular with the intrinsic alignment effect and the clustering fossil, we expect to see some effect from the gravitational wave. And in particular, I want to stress that clustering fossil is important because otherwise we expect a zero signal there, right? So it's relatively foreground or relatively systematic, clean way of detecting spin 2 field from the galaxy survey or large-scale structure. Thank you.
Questions? I actually had one. So if you go back, you had that plot with R across in the surveys. Yeah, right there.
Yeah.
So how does that scale with R? Is it quadratic in R?
I think it's linear.
Oh, it's linear.
Yeah.
Dong-hee, could you go back to the slide where you show the intrinsic alignment from gravitational waves?
Yeah.
The angular power
Yeah.
spectrum.
Here.
Right. Or maybe the next one where you compare to with the second order scalar.
Okay. Yeah.
Right. So I think the intrinsic alignment induced not by gravitational waves but by the scalar gravitational potential is of E type, right? And then this intrinsic alignment, when you observe it, will be further distorted by gravitational lensing, also by scalar potentials. So is this signal already considered here or not?
So you're asking?
Just like in the CMB, you have spurious B mode from gravitational lensing that converts some of the E mode polarization pattern into B mode polarization pattern. So here, because we know that even without gravitational waves, the scale large.
Oh, I think that is in the second order geometric equation part.
It's already included in. Okay.
Right.
More questions? Okay, let's thank Dong-hee.